Good afternoon, everybody, and welcome to all of you. Today's presentation will be performed by Lee Chinitz, the CTO from octoScope, and the topic of today will be testbeds for 5G wireless performance testing. This being said, Lee, the floor is yours.
All right, thank you very much, and I guess mostly good afternoon, everyone. So I am Lee Chinitz. I'm the CTO at octoScope, which is a company that builds wireless test solutions, including test beds, which is the topic of the presentation today. Actually, I thought I'd start off with a little bit of an interactive piece here. So I wanted to maybe pop up the first question here, which I think is a question about how many of the people on the call today actually use test beds in their wireless testing. I'd be interested to know that. All right, so the general topic today, right, is wireless test beds for 5G wireless performance testing. So there's a few words in there that we need to talk about. There's 5G, and this is not a presentation on 5G and what it is, but we should talk about it a little bit in the sense that it is important to the general topic of how test beds can be used for performance testing. There's a fairly common refrain which people use when talking about 5G, which is that 5G is going to change everything that we know about everything. I'd like to maybe throw a little bit of maybe reality into that statement and talk a little bit about things that won't change because they are more general from the point of view of testing wireless devices. And then talk a little bit about performance testing, since that is the general topic here. I mean, what is it? What's it all about? And then kind of bring those two together. So 5G and performance testing, and what makes performance testing of 5G a challenge. And I've got a big list here. I'm going to go through a lot of those in the presentation today. The many frequency bands, handovers that are going to be required, technologies that are embedded in some of the higher frequency bands, like mmWave bands that are part of 5G, the new applications around things like IoT, and also very interestingly, the new regulatory regimes that 5G is getting into around shared and unlicensed spectrum. I don't have specific section here on test beds, and the reason is I've tried to sprinkle the test bed conversation all through the discussion. So as we go through, I'm going to kind of mention test beds and show how they can address the various items that I'm discussing. Okay, so let's move on then. So quick touch base on 5G, right? This is one of a million slides that are available to talk about what 5G is, right? It's a whole bunch of new services and applications. It's intended to support, very, very high speed access. It's intended to support the IoT. It's intended to bring us new mission critical applications. So there's many, many things. But there are, I would say, three main categories that have kind of coalesced out of the 5G discussions, and they're shown on this slide. And they start with enhanced mobile broadband. So enhanced mobile broadband, that's really the part of 5G that's kind of the more of the same, the evolution from 3G to 4G to 5G, right? So enhanced mobile broadband says we're going to be able to do the same things we do now with 4G networks. We have videos and other kinds of streaming applications. We're going to now have access to enough bandwidth to do 3D video and ultra high definition screens. So very high data rate kinds of applications. So the next application that people talk about related to 5G is listed here as massive machine type communications, or really what people refer to as the massive IoT. So here we're actually talking about a very different kind of application, right? We're talking about endpoints that are not even necessarily humans. These are just devices. These are devices that may not even have a lot of data to communicate. They, may not need, gigabytes per second of throughput. On the other hand, the number of devices is expected to be very, very high. So we're talking about extreme density, the need to support that. And then finally, a very interesting area around these ultra reliable and low latency communication applications. So, here we're talking about systems where the endpoint, the wireless endpoint, needs to be able to take an action and understand the result of that action very, very quickly. So things like self-driving cars or remote medicine, even futuristic ideas around people doing, let's say, remote surgery. So, the idea there is that any action taken on one end of the link needs to know very, very quickly what's happened at the other end. We can't have long latencies. We need to have very, very quick response times. So again, what's commonly said about 5G is that 5G is going to make everything different, right? You can see it's shown in this path from 1G up through 5G, where 4G in this little picture is shown as just a person jumping over a hurdle, and now in 5G we're on a rocket ship in what appears to be a very unsafe way of riding on a rocket. But at any rate, it's supposed to be a huge difference, and it's going to fundamentally change everything we know. So not to be the old guy in the room, but I want to ask, is everything really different, right? There are some things that every wireless technology does, and from our perspective, 5G is really not going to be different in that way, at least at this highest level, right? Wireless devices still need to conform to regulatory requirements and other requirements for the technology. So there'll be testing that's known as conformance testing. Wireless devices still need to interoperate with each other. So there will be interoperability testing to make sure that interfaces are implemented correctly, so that systems can be deployed with multiple vendor solutions, and the devices will behave properly. And then finally, kind of the topic of today, there's performance testing, right? Performance testing just makes sure that devices perform, I don't know if this is just an American phrase, but kind of up to snuff. And the definition of that is variable, right? There's no regulatory requirement usually that says how devices have to perform, but operators may have their own requirements, or end users may have requirements. There could be standards bodies that put requirements into place. We're seeing more and more of that these days. And so, all of these things will happen. And the example that what occurs to me when I think about this idea that, everything is going to be different is that no matter which technology generation we've been talking about, we tend to have the same conversations over and over again. So for example, right, anybody who's been around long enough remembers that when 3G was deployed, there was a whole big conversation. I mean, there were panels and meetings where people would talk about 3G versus Wi-Fi, right? Who was going to win? Was it going to be 3G or Wi-Fi? Not surprisingly, that same exact conversation happened when 4G came out. And guess what? Now we're wondering if 5G will kill Wi-Fi. Looks like Qualcomm thinks it might. So, just from my perspective, it's actually important to remember that there are some things that actually just stay the same. And so performance testing is something that really has been done for wireless systems, I say, forever, right? I mean, it's always important to know how well devices perform. And so I think that from the point of view of 5G, what's really interesting to look at is what's been done for performance testing, what's being done now, and how does that apply to 5G. So performance testing, unlike interoperability testing, conformance testing can be fairly complicated, and people have a number of different ways of going about it. So let me give a little bit of context to the idea of performance testing. What you're interested in when you're talking about this is, again, based on the phrase itself, how does the device perform? How does it handle whatever application it is you're looking for it to handle under conditions that it might experience? So some ways that people kind of try and understand this. There are anechoic chambers where people put devices in and test links. Anechoic chambers are really good for getting extremely clean measurements of device performance. They're very good because if you look at this picture, for example, you can see walls covered with absorbing foam, conical shapes. All of the reflections are being damped down. It's extremely clean environment. There's no interference. You get very, very repeatable measurements. You can measure the performance of device or, at least antenna patterns all around in multiple angles. The downsides of this is that, they're very big, they're very expensive and complicated to use. They're hard to share. It's hard to get access to these things. And of course, they're not a particularly realistic environment. They give you a sense of how a device will perform under these extremely ideal conditions, but not necessarily a good idea how they're going to perform, in real world environment. So at the other end of that spectrum is the idea of doing walk testing or drive testing in a real environment. The pros are there, right? This is a lot easier and cheaper than using the kind of chamber that I just showed. The measurements that you get are, going to tell you how devices perform in the real world. So those are very, very good things to know. On the other hand, you're out in the real world when you're doing these tests. So it's extremely hard to repeat a test like this, at least precisely. You can get kind of general results, but interference conditions will change, local conditions will change, and it's just, multipath will be different. You would be very hard pressed to get a repeatable test time after time in a walk test or drive test. There's some other ways, and these are even more kind of out of reach for most people. There are outdoor antenna ranges, which again are not particularly realistic environments. They're at least not quite an anechoic chamber, but again, they're extremely difficult to find, and only very sophisticated users tend to have access to these. So one of the things that has been happening recently, and we certainly see it in our business, is that there's a kind of combination of all of those things that has come together, and it's we call it a personal test bed. I have a little survey question here, which is just to find out how many people on this call are actually familiar with octoScope. So I'm not going to spend a lot of time talking specifically about octoScope products, but I'm interested to know how many people know about octoScope. But what these test beds are, and I've got a picture of one here on the right of the screen. What these test beds are kind of a combination of kind of the best of all of those testing mechanisms, kind of performance testing mechanisms that I just talked about. They are, as you can see, multiple chambers with that, absorption, kind of material that is keeping the internal environment quite clean for the most part. And these test beds are all kind of linked together in ways that we'll discuss a little bit later. But the important part about this is that rather than having to go out into the world and do drive tests or walk tests, you are able to put your devices into a test bed that is local and easy to access. So you're able to do tests, performance tests that might take you days or weeks to do in an open air environment, and those tests can be done in minutes or hours in a test bed like we're showing here. Again, because it's small and compact, and because you have the very clean internal environment, you're able to generate an extremely ideal RF environment to start with. But unlike typically what you're doing in kind of a large anechoic chamber, you're then able to introduce real world impairments to that RF environment and see how the device will perform. So you get kind of this combination of a clean RF environment with a walk test like real world aspect to it. And then finally, a very important aspect of these kinds of test beds is that they can support multiple bands, which again is something that's very important from a 5G perspective. And that's kind of the area I'm going to get into first. This concept of multi-band and especially millimeter wave kind of testing. So in general, though, at the highest level, what's important about a test bed? If you're going to use a test bed, what's important is that it should be able to produce repeatable results. So, like those big anechoic chambers, I said that was one of their big, pros. And I did mention that in a real world kind of walk or drive test, it can be very difficult to do. But a test bed is expected to be able to produce these repeatable results. What you want is to be able to run a test, run it again, and get the same results. If you run a test, run it again, and don't get the same results, then you really don't know what you've learned from that. Now, if you're not getting repeatable results, the reason could be actually the device that you're testing. So, or the device under test. I use this acronym, the DUT, I think several times in this presentation. That's what it refers to. Also known in some cases as an EUT, the equipment under test. But there's really two things that can cause test result instability. One is the device itself, and the other is the test equipment. Now, if it's the device itself that is unstable, that's at least a useful thing to know. You've done a test and you realize that you've got a device that doesn't give repeatable results under the same conditions because it itself is unstable. If it's the system itself that's unstable, that's just a problem. So kind of key to the whole idea of these wireless test beds is a stable, reproducible environment. And I'll talk about that again a little bit later.
Lee, I have to interrupt you quickly. There is one question that popped up from the audience during one of the previous slides. And the question goes, how do you account for positive impact of reflection? And then between marks, there is multipath.
Right. So you can see in this test bed, and again, I know we're not doing a product overview here, but in this particular test bed, you can see this kind of blue absorption material. So the that material is designed to damp down reflections from the walls by something like 20 dB from a reflection point of view. So when you're looking at actual path loss from device to the wall, 20 dB of reflectivity, and then coming back, the multiple paths are quite far down. Okay, so I think where I was, in the discussion there was to say that so performance testing. I think the message I'm kind of trying to make here, right, is that yes, 5G will change everything, but there are some things that just remain the same, and performance testing is one of them. So performance testing is not a new thing, as I just showed, right? It's been going on forever. There's many ways of doing it. These kind of multi-chamber environments are really catching on with the industry these days. But it's also fair to say 5G does actually introduce some challenges into that testing environment. So let's talk about why. One of the important reasons is that 5G, unlike, let's say, 4G, 3G, where it was fairly clear kind of where these technologies were operating, 5G is basically a unified air interface that operates across many, many bands. And one of the key ones, especially one of the key ones that introduces some challenges for testing, is mmWave operation. So just really quickly, here's a picture that is a fairly common type of picture that you'll see when people talk about 5G. And what this is showing is that you will have networks deployed that may use low frequencies, let's say around 700 megahertz for wide area coverage. You can see these big purple blobs that have covered, kind of everything. Then you may have kind of, this as high frequency. I tend to think of them as more sort of mid-band frequencies, let's say 3.5 gigahertz in that range for spot coverage. And you can see that happening, here where you need higher throughput, for example, but you're not going to get the same type of range. So this will be happening in very specific locations. And then on top of that, where you have, for example, extremely high density applications or extremely high throughput requirements, you may also overlay millimeter waves on here. So this is showing 26 gigahertz, for example. So we've got this requirement to be able to look at let's say 700, 3.5, and 26 gigahertz all in kind of the same system. Got another question here at the bottom, so you can pop that one up. I think what I'm interested in learning about here is what 5G frequencies people on the call are interested in. But the comment that I'm making here, and this will actually sort of carry throughout the presentation, is that really spectrum flexibility is one of the hallmarks of 5G. 5G, really covers the gamut from unlicensed spectrum, which I'm going to touch on in a little more detail at the end of the presentation, through shared spectrum. So at least, especially in the United States, we're looking at that in a whole new regulatory regime at 3.5 gigahertz and millimeter wave spectrum. So there's quite a big range of regulatory regimes and spectrum use that people talk about with 5G. So what does that mean? What I'm gonna do here is kind of go through, when I talk about what 5G kind of brings to the table. I'm gonna talk about how what the requirement that is that places then on test beds, if you can use test beds to do 5G performance testing. So I'm showing a picture here, and by the way, I just want to be very clear, this is not a coverage map in any realistic operator. I completely made this up just from an example point of view. So it's very similar to the one I showed before, that sort of graphic with the 700 and 3.5 gigahertz and 26 gigahertz overlaid. This is a very similar thing. So, first of all, 5G performance testing is just going to need to be able to test in many different bands. So, for example, you will get deployments, again, similar to the one I showed before, where you've got, a low band, broadly deployed, kind of coverage layer. You'll have a mid-band deployment, which is focused on slightly higher density. And then, for extremely high density locations or high bandwidth applications, you may have, a millimeter wave application. So one of the requirements then for test beds is that test beds actually be able to test in multiple bands. I've got another question here that you can pop up. So what I'm interested in knowing here is, whether or not, again, in addition to what frequencies people are looking at for 5G, whether or not there's actually also interest in multiple bands simultaneously. So what I'm showing here is the inside of a test bed that is actually designed to do exactly that. You can see these kind of large low band antennas. These are cellular antennas designed to cover kind of traditional cellular bands. You can see there 700 megahertz, 1.7 gig, et cetera, et cetera. There's kind of broadband antennas designed to cover the whole mid range, so it'll certainly cover 3.5 gigahertz, as well as other bands that are important. We'll talk about later, unlicensed bands, especially 5 and 6 gigahertz, which 5G is very active in. And then, of course, millimeter wave operation shown here with these millimeter wave antennas. So in addition, it's really not just antennas that need to be taken into account. It's really the whole test bed solution. So the RF connectivity between the antennas and the rest of the system, attenuators that are going to be used to attenuate the signals. And I actually have a demo a little bit later where I'm going to show how those attenuators are really used. But roughly what we're talking about is the ability to move signals from one of these chambers to another of these chambers, and change the signal levels as you go. Those attenuators, just like the antennas here, are sort of RF specific, frequency specific, and so you need different attenuators in order to handle the different bands. So it's really the whole system that needs to cover it. But that is, one of the requirements that gets added to these test beds as we move into 5G performance testing. So in addition to just having multiple bands, like saying well, there will be 600 or there will be 3.5 or there will be 2.6, it's also, important to, when you're doing performance testing, look at how devices are going to handle the transition from one band to another. So roaming becomes a very important test. It's already a very common test that people do in test beds, and I'm going to talk a little bit about how. But this kind of multi-band roaming is really a key aspect of performance testing in a wireless test bed. I mean, it's a key aspect actually of 5G performance testing in general. But I think what's maybe interesting for today is to talk about how that can happen in a wireless test bed, which, again, you saw it before. It's a bunch of chambers, looks very static. So, how can it actually do this kind of roaming, this kind of very dynamic thing that you might think is something that you can really only do in a walk test or drive test environment. So I want to give this is a very, very simple example. I kind of like the animation because I think it helps explain how these test beds are much more dynamic than they look. And again, as I said, this is all leading up at some point to, I'm going to do a demo for you, kind of a live demo of the system, and you'll see this actually happening. But imagine a situation in which you've got, let's say, a small cell, providing coverage in an environment. And what you'd like to see is something like how multiple users will interact with that small cell. So you may have those users, kind of all show up at the front of the building, and they're very close to the small cell, and then they're going to scatter around the building, right? And you'd like to see what that looks like from the point of view of the wireless environment. Now, how would you do that if you've got a test bed similar to the one I showed before, made up of a bunch of chambers that don't look like they move, right? What you'd like to do is something like this, right? You've got, your small cell in one of these chambers. Now you've got your user devices, your user equipment in different chambers, and you kind of want to do the same thing, right? You'd like to move them close and then have them all kind of scatter around and get further away, and you can see how that behaves. But of course, you're not going to do that, right? But the nice thing about these chambered environments is that we don't actually have to move the chambers to do any of that. We have all the chambers connected via these programmable attenuators that I mentioned before. And all we need to do is change the attenuation. So a low attenuation, for example, on this link means that this user device is quite close to our small cell, whereas this high attenuation on this link means that this user device is very far, quote unquote, far from an RF point of view anyway, from our small cell. And because the attenuators can be tuned and changed in real time, we can actually, effectively move the devices and create these mobility scenarios like the one I was showing before, where we have device moving from one frequency coverage area to another frequency coverage area. So, that lets us do, kind of mobility and handle multiple different frequencies in our 5G testbed. But, it's not completely fair for me to say something like, well, problem solved, right? We just put in different frequencies and you're all set, right? Because not all bands are the same. I think it's probably fair to say something like, 1.9 gigahertz is pretty similar to 3.7 gigahertz. So, I'm not that concerned from a testbed point of view. But one of the major, kind of different aspects of 5G is that it's making heavy use of mmWave bands. For, especially for things like this enhanced mobile broadband area, right, where you're talking about connected cars and something like that, where you have very, very high data rate applications. You need, a lot of information being transmitted, and some of the other benefits of very wide bandwidths. So, how does that affect a testbed, and what does a testbed need to be able to do in order to do performance testing for these bands? One of the things that you also get with millimeter waves, by the way, is much smaller wavelengths. So very small antennas, meaning a lot of them per device. And this is enabling these, massive MIMO and beam forming and beam steering kind of applications. So, first of all, just really quickly, to illustrate the point that, there's quote unquote a lot of spectrum available in the millimeter wave bands. Like, why do you want to use them? I just want to point out, if you just start adding up the amount of cellular spectrum that's generally available in all these different bands, and this isn't a complete list, but it's roughly a gigahertz of spectrum. You start adding stuff up here and there, you get up to about a gigahertz. If you then put on, some of these other bands, 2837, up to 60 gigahertz, you're talking like 11 gigahertz of spectrum. It's a huge amount of spectrum. It's much, much more, which is when people say, you need to go to the millimeter wave bands in order to get all of this bandwidth. That's what they're talking about, right? It's a lot of spectrum. But the physics of that spectrum is really different. Again, it's all RF, and so it's all, kind of governed by the same, basic equations. But in reality, when we're operating the millimeter wave bands, we are looking at technologies, like I mentioned, like beam forming and beam steering, that are absolutely required in order to make this stuff work for a real kind of wide area deployed wireless system. Again, just quickly, people are probably quite familiar with these kinds of things. Millimeter wave bands do have, unique issues. Kind of as you move up in the spectrum, you start encountering things like resonance issues between the frequencies themselves and, molecules like water molecules and other kind of gaseous molecules that they will encounter in the world, and therefore they cause an enormous amount of loss. So that's what this little red line is showing. You see, like, for example, 60 gigahertz, an extremely high absorption of the RF by the environment itself. In addition, as you get higher and higher in frequency, things become more and more like light. Therefore, you get very, very sharp edges. So millimeter wave technologies tend to behave a little bit less like what we think of as kind of classic RF, where they are bending around the edges of surfaces, and more like they're casting shadows. So you get a lot of issues related to non-line of sight and things like that. And actually, even if you forget all of that stuff, if you just look at the basic path loss difference between, let's say, 40 gigahertz and 1 gigahertz, this is a very simple, equation between the two. There's something like 32 dB of path loss difference. So that's a factor of 1,000, more attenuation when you're up at, let's say, 40 gigahertz. So, there's some challenges, right? So what does it mean? It means that it's hard to get range in the millimeter wave bands. It's hard to get a lot of distance between your transmitter and your receiver. It's hard, but it isn't impossible. And the reason it isn't impossible is that you get some of these benefits from millimeter waves as well, which is these very small antennas and the ability to pack a lot of them together. And therefore, the ability to apply beam forming, beam tracking, beam steering, lots of these technologies in order to overcome these range and kind of non-line of sight issues. So there's a lot of work that's been done there. There are a lot of people who will talk about, how this is all possible to do. But from a testbed point of view, that has implications. So, one of the implications of all of this is that more and more for millimeter wave testing, all of the testing is going to need to be over the air. So I wrote OTA here. It refers to over the air. I'm distinguishing there between over the air testing and conducted testing. It's been the case that, in addition to the kinds of testing I mentioned before with, anechoic chambers or walk testing or drive testing, which is all over the air testing. People have also done testing where they'll just hook the antenna ports of a device up directly to RF cables and do what's known as conducted testing. They can, you can run those signals through channel emulators and try and emulate the environment, et cetera, et cetera. You can do all those things when you have a few antennas. But, with millimeter waves, that is becoming less and less possible, frankly. If you look at the bottom of this slide, what I'm showing here is a 256 element array, the size of not significantly larger than the size of a US 25-cent piece there. So it is, it's quite small. It's got a ton of antennas on it. And there's simply no really practical way anymore of thinking about, connecting those antennas up and doing conducted testing. And you really need to be looking at the ability of these devices to do, for example, beamforming testing. So, what we're hearing more and more, is that people doing 5G millimeter wave testing want to look at over-the-air testing capabilities. So I'd like to give just a couple of examples of things that we have seen as a testbed company, people coming to us and saying, here's a test we'd like to do. So here's one, for example, where we've been approached and people have said, look, we have one of these very highly integrated antenna array RFIC devices, and what we'd like to understand is what is the beam forming, beam steering capability of it actually look like. So what we'd like to do is we'd like to be able to generate phase signals on our array, and we would like to be able to measure in a test bed what the resulting beam looks like. How well is it steering? So through the use of a set of probe antennas that are shown on the right-hand side of this, we can actually, look at that beam and understand how that beam steering and phasing is working for that device. Another example of requests that we're seeing in this area would be one like this, where we have two chamber solution kind of shown there on the left, and inside have in one of them a G node B and the other a UE, and the chambers are connected again via these mmWave appropriate horn antennas, mmWave appropriate attenuators. And the idea is to be able to move, for example, the UE, or maybe the UE and the node B on built-in turntables, so that what we can test is the ability of the devices to actually form and maintain beams between each other, even as they're moving. So we do see requirements being placed on the test beds that are specifically a result of the kinds of new requirements that are coming into place for 5G, based on the fact that mmWaves is such an important aspect of it. And then there's yet another layer of complexity that's involved with 5G performance testing, which is that 5G networks are unlikely to be deployed, at least initially, kind of all by themselves. They're likely to be deployed on top of and in conjunction with existing, let's say, 3G and 4G networks, and even other technology networks, which I'll talk about a little bit later, from an offload perspective. So again, there you're going to want to be able to test things like, motion, and not only, between, let's say, 5G technologies across different bands, but, even other technologies, 4G technologies, et cetera. I have another question here. I'm kind of wondering, what are the technologies that people on the call are also looking to test. So it's important to be able to look at that as well. And again, these are the other kinds of requirements that we see from a test bed point of view. Then, in terms of what people want to be able to do. So I'm showing here a test bed where in the test bed we've actually included not only, so in this case specifically Wi-Fi, because there was an offload aspect to it, 4G LTE signal coming in, and a 5G G node B is there as well. And then what the customer was really interested in looking at was how a specific device was able to handle mobility across all of these different technologies, based on various things that would cause the device to move, but primarily just signal strength, which again we can cause to happen by modifying the perceived signals of the different networks at the UE by changing these attenuators. And again, I'm kind of leading up to a little demo of all that very soon. From again.
Lee, small interruption. Yeah. There is another question that came in from the audience, and it goes like this. What about IoT devices that use 5G? Are there differences in testing them versus mobile phones?
That's an excellent question. I am going to touch a little bit, I think, on IoT, but let me see if I can just kind of answer the question. I mean, there are so IoT devices that use 5G specifically. I think the probably one of the main things that people are interested in from an IoT perspective then would be things like, first of all, maybe fairly dense testing, the ability to test a lot of devices simultaneously. And the other thing would be things like, and we see this as well. We're seeing this now in some aspects of Wi-Fi testing, even where Wi-Fi is attempting to position itself as a better IoT technology. So things like power saving modes, those tend to be less critical from a cellular telephone, mobile kind of testing environment, where people tend to be more interested in the kinds of things I've been showing, like throughput and roaming capability. Whereas with IoT, we get a lot of questions about can we test that that power saving modes are working well? Can we test that that the device is able to actually sleep and wake up on a schedule and maintain long battery life, things like that.
That's the second question just came up. Yeah, I'm sorry, and it goes like, how about testing mesh communication capabilities? How about that?
Yeah, good one. That's actually the demo I'm leading up to. So if you want to just hold that question, but yes, we see mesh testing being more and more of a requirement. We get more and more questions about it. And, by the way, it's not just us. If you look at what's going on out in the industry from the point of view of standards, again, we know a lot about Wi-Fi testing from our company perspective. There's a Wi-Fi Alliance, what's known as Easy Mesh protocol that's being standardized and put out for certification testing. But therefore, we get a lot of requests for people to be able to test that. We also see places like the Broadband Forum and the Wi-Fi Alliance and even Etsy now, people putting together test plans designed to look at mesh testing. So I'm going to actually show, I tried to lay the groundwork a little bit before for how these test beds are much more dynamic than they might initially appear, if you just think of them as a bunch of boxes, but they're actually a bunch of boxes with very dynamic connections between them that do allow you to test mesh. I'm actually going to show you some of that.
Leah, I'm sorry, but I'm not allowing you to go to this slide, apparently, because another one came up. What about handoff testing?
Yeah, I mean, it's what I was showing before. I think at least I was implying before, right? We have customers like this one, right? I mean, this one I guess is a handoff test. If you if by that you mean I'm handing off between, for example, I'm doing let's say a Wi-Fi calling handoff to LTE. This is the example here, but it doesn't have to be that, right? It could be LTE to 5G. Now, if what you're talking about are multi-operator handoffs, I mean, again, people have different terminology. I'm not quite sure what the question means. Just handover, handoff, things like that. If you're talking about multi-operator, there's nothing preventing you from doing a multi-operator test here, but it does require, even as shown in this diagram, it does require kind of a back end. So, if you had, for example, a 5G network from one operator, here, and then not shown, a 5G network over here from another operator, you could do that test as well. But again, it just requires a little bit more kind of infrastructure support to do it. So from our point of view, again, not a product presentation really, but what we do, we are very, very, strong in Wi-Fi testing, and we have a lot of capability in our Wi-Fi visualization. So when people are looking, for example, at throughput testing in an octoScope testbed, we provide a lot more, information than just throughput. Throughput may be the metric people are interested in, but the underlying attributes like the signal level, the PHY rate, what MCS, how many streams, what bandwidth, what's the congestion look like, all these various things is information we provide. I believe that similar insights are going to be valuable in multi-band, multi-protocol, multi-technology 5G test beds. People will want the same kind of information. So to get to, I think some of the questions have been asked, things like, handoffs, mesh, that sort of thing. And I kind of laid the groundwork a little bit for it before, right? But, and again, this isn't different from other generations. 5G needs to support mobility. But with IoT, a little bit to the point of one of the questions there, there's actually a lot more things that are going to be moving around, and some of them are not even things that have people attached to them, right? There's, like in this picture, right? There'll be, maybe cars, there's light posts that will have 5G, they'll be talking to each other, things will be moving relative to each other, some things aren't moving at all. So, mobility and the ability to test a motion is an important attribute of a test bed. So let me get into this and do the actual demo that I wanted to do, which hopefully will at least give an initial idea. I mean, we don't have a lot of time here today. Anybody who wants to get into more detail, more than happy to do that. But in a test bed like the one shown here, this is the same basic test bed that I showed in that big picture before. We're actually able to do a lot of what we're talking about in terms of mesh, handoff, mobility, and also the one aspect I want to point out here is really to emulate the whole kind of walk test, drive test environment in a realistic way. So we can actually record a motion pattern as a device moves throughout an environment. So, this is a walk test example. It doesn't have to be a walking, but in this particular case it is. So we may have a mesh shown here. We may, walk around in that mesh and record what the attenuation profiles look like. And we can then play that back in our test bed in this way, right? We can have a UE in one of these chambers. We have these attenuators that have the ability to be controlled and again are very, very dynamic. And we can actually play a realistic. So we're not talking about kind of a simple, I'm going to change the attenuation by 1 dB every second or something like that. I can do a very realistic change of attenuation through these attenuators, so that my UE sees, for example, one base station and another base station, maybe of different technologies, maybe on different frequencies. Doesn't really matter, even maybe to the point of the question before, I'm not sure, maybe even from different operators. And then I can actually watch the behavior of my UE as it goes through this. And this is a very flexible technique that can be used, again, not just for a single technology, single frequency, but for different frequencies, different technologies, the kinds of requirements that 5G really places on the test bed. Let me show you very quickly what that looks like. Let's see if I can get to it real quick. So this, and again, not a product presentation, I know, not enough time to get into details here, but this is the user interface for our test bed. And what I'm going to do is do what I just described to you, which is I'm going to take a UE and I am going to play realistic attenuation profiles through the test bed, and I'm going to watch the UE as it moves from one device to another. So the test is actually started. What you're looking at on the screen right there is the end result, but the test is now running. So what you're seeing, over here is kind of our whole setup part. But the thing I want to highlight to you, you're looking at throughput of the device, by the way, as it moves through the system. One thing I want to kind of highlight here is you can actually see the access point to which it's attached. If you look, it's the one with the MAC address that ends in 37BD. And if you're looking on the screen just to the right of where my cursor is, you can see the RSSI beginning to drop as the motion profile is played through the attenuators. And I won't make you watch this whole thing, but I will let you see kind of the first handoff, and you can actually see it happen. If you watch the ID of the device, the 37BD. Oh, it's now at 37B9, and you can see why. So you can see that the device, started off as the connectivity of that device got poor. It handed off right here, and we went from 37BD to 37B9. It'll keep going, and we can come back to this later, but I don't have enough time to let you go through the whole thing. But basically what you're seeing now, right, is this very realistic, not a simple ramp, but a nice, realistic model of a walk test. In this case, could be a drive test, whatever. And again, just to highlight over here on the right, I mentioned before, we give a lot of detailed statistics around Wi-Fi. You see the throughput, but you can also see the signal levels, the data rates, the MCS, that sort of thing. And again, I think testbeds will be called on to do more of that for 5G technologies as well.
Yeah, and another question popped up from the audience.
Sure.
And it's, how were the test profiles created? And it's about the small demo you just showed us.
Those were done actually. This is actually a reasonably accurate description of how that was done. In this particular case, a UE was walked through the environment, and it was recording the signal levels from all of the devices as it moves through. And then what we do is we simply play back those we create attenuations such that the signal levels seen by the UE in the testbed is equivalent to the signal level seen by the UE in the real environment. So again, it's done by essentially a recording phase to create the model. And then the nice thing is that we can just play that model over and over and over again as we modify the devices, as modify the roaming behavior protocols. We can speed them up, slow them down, do whatever we want. And to go back to an initial point that I was making, it's then quite repeatable. So unlike if you tried to do this in the real world where you just walked over and over again through an environment or drove over and over again through an environment, the environment itself would just be changing. And, again, you would learn something, but it would be very difficult to say, I just did the same thing, over and over again. Whereas in this case, you absolutely can do the same thing over and over again, exactly the same thing. So let me touch on one final thing, which I think is quite important from a 5G test bed, wireless performance aspect. And that's the concept of unlicensed operation. So 5G is really the first technology, the first, cellular technology that has real support for the use of unlicensed technologies. It's not the first to ever use them. We all know about things like LTU and LAA and multi-fire, but from a standards point of view and from the point of view of, not anchored, but, standalone unlicensed operation, 5G NRU is really the first. And that, again, leads to some fairly interesting, issues around test beds and what they need to be able to do. Because, testing links, like I just showed, a link between here and there, that's all great. But, when you're talking about unlicensed operation, you also need to wonder, kind of how is that link going to work when it's in an environment with like everybody is talking to everybody else. This is maybe related to the IoT question that was asked before, especially if we're talking about, IoT devices or 5G where you're talking about unlicensed operation. I have a question down here at the bottom. Interested to know, people on the call, what other technologies are people, looking to test. But, the challenge then for the test beds is to be able to create an environment where you can test not only, whatever 5G technology you're looking to test, but, create an environment in which you can also handle, all of the other technologies, especially, again, in the unlicensed bands where, you need to be able to operate. So I think one of the really interesting scenarios that is going to come up, is already on everybody's mind, is sharing in the 6 gigahertz band, so N96. I think it's very likely, seems very likely to me, certainly, that both Wi-Fi and NRU are going to coexist in 6 gigahertz band. We're going to see both of those for sure. There are a lot of coexistence scenarios then they're going to have to be able to be explored, right? There's kind of simple ones where you've got, let's say, a Wi-Fi situation over here and an NRU situation over here, maybe some slight overlap. You can take a look at what, the coexistence looks like between the two, but there's going to be a lot more complex ones than that, right? Where, there's not a sort of a clean break between the two. There's going to be, complete overlap. The devices near each other, far from each other, whatever it might be. So even the simple scenario of just, one AP, one station, one UE, one node B, will have a lot of different variations that are need to be tested, right? They could be close to each other. They could be far away from each other. Maybe just the station and the UE are close to each other. Maybe just the AP and the node B are close to each other, whatever it might be, right? So there's all kinds of variations that are going to need to be tested. And at least in my opinion, coexistence testing really needs to be defined in the context of a test bed, because from my experience, it's kind of the only good way to have a productive conversation about coexistence scenarios. Anybody who's ever dealt with coexistence before knows that kind of the first thing that happens when people present results is that people immediately jump on the environment in which the testing was done. They say, well, this is not valid. You didn't do this. You didn't do that. I don't know what this is. I don't know what that is. It's really hard to have productive conversations. But, in the context of a test bed, you can. There are a lot of different, let's say, test beds or, kind of testing areas that you can look at. There's ANSI group that has kind of made a point of doing coexistence testing, and they call out all kinds of different options like conductive testing, and like I mentioned before, these big anechoic chambers or open air testing or multi-chamber testing. But the important thing, no matter what it is, right, is that the tests need to be able to cover the scenarios of interest. So they have to be extensible to handle, kind of whatever test environment you're interested in, coexistence environment. And they need to be repeatable. And I've mentioned that so many times, I won't really dwell on it. Another thing, though, is that, at least in our opinion, test beds really should be accessible, right? So again, I mentioned before, large anechoic chambers, great for certain things, really hard to get your hands on. And so anybody who wants to kind of do that testing, can't really do that. From the point of view of coexistence between Wi-Fi and cellular things operating in unlicensed bands, this has been done, at least to some extent, by the Wi-Fi Alliance, where they looked at coexistence between Wi-Fi and LTE-U. So they used the kinds of test bed that I've been talking about a lot today, which is this multi-chamber, kind of highly connected, fully meshed test bed. And you can see a picture of it there. I'd say, in my opinion, and I made this point before, the only really good way for the industry to have productive conversations on coexistence in between, 5G and other unlicensed devices is going to be if there is an agreed on test bed configuration. Again, I think it allows a shared reference. It makes it possible to create those very simple AP station G node BUE pairs with any kind of topology that you're really interested in by making use of these attenuators, and then changing them via software. Very, very simple way to look at any other topology that you're interested in. And also, you can then, anybody else who's interested in reproducing your results, checking your results, understanding, what their, specific changes to the protocol would do in your situation, only needs to know, okay, what is the topology you set up in this testbed, and then they can set up the same thing. And then even many, much more, depending on what's desired, you can have much more complicated scenarios. Like, for example, because in Wi-Fi, certainly we're seeing a lot more meshes. So like a 3-node mesh and a station, along with a G node B and a UE. Again, very simple to set up that kind of topology in a multi-chamber testbed. So to wrap up, I know I've gone a little bit long. I do apologize. From a performance, from the point of view of performance testing in a wireless testbed, different areas of 5G are going to require different kinds of capabilities. If you look at just basic sub-6, 5G, there you're talking about fairly what I would call standard things: rate versus range, interference, multipath, and motion. These are things that testbeds do now. Hopefully I gave you kind of a sense of that. Once you start layering in mmWave, right, then you've got some new functionality that you really do need to be able to handle. Hopefully I gave you a sense of how, we see that requirement coming up and the kinds of things, we're doing to address the needs for example, beam forming and beam steering kinds of testing. Once you then layer in new regulatory regimes like shared spectrum or use of unlicensed, coexistence becomes a major issue. Again, hopefully kind of laid out a little bit what a testbed would look like in order to do coexistence testing. In fact, again, it's been done already for LTU, and I think for 5G it's become more and more critical. For multiband testing, roaming becomes an issue. Hopefully that demo gave you a sense of how you can set up a testbed to actually roam devices around through different access points. And then multi-technology, offload becomes, key. Being able to look at, again, not only 5G technology to other 5G technology or different bands, but, even handing off between technologies. So, for example, Wi-Fi offload, kind of a major part of 5G, frankly. So again, in quick summary, as wireless becomes more and more critical, performance expectations go up. I mean, again, kind of obviously, right? I mean, if you're talking about doing things like, important medical procedures over wireless, this is no longer just like, can I reach YouTube, right? These are mission critical applications, right? If your car is depending on the wireless network, for self-driving, that network really better be solid. So performance testing is really becoming more and more important. And so the implications then for testing are quite profound as well. Everybody needs to be able to do testing to make sure that everything performs in a very crowded and complicated wireless environment with technologies that really make it important that you do testing over the air, not just conducted testing. So companies, are rising to the challenge, I think, to provide test tools, and there's going to be a lot of them. It's all, there's a lot of different things that people test, but wireless test beds, and I hope I've kind of made this point, are becoming more and more really a key element of that testing strategy. So with that, I know we went over. If you found information interesting, useful, feel free to contact me, contact us if you have other questions you want to discuss. But thank you for attending today.
Thank you very much, Lee, for this extremely interesting presentation. Also, a big thanks to the audience for being with us. As Lee said, if there are any questions from your side, please do not hesitate to contact Lee. The contact details can be seen on the screen, or you can always contact CN Rood directly as well. We would be very happy to help you further. Thank you once again. Bye-bye.